Dr. Chen, thank you so much for joining us this evening.
Hi, everyone. It's a pleasure to be here today. So let me go ahead and start sharing my screen. I think this is going to work. Let's see. Okay. Can you see my presentation?
We're all good.
Excellent. All right. So it's a pleasure to be here today. My name is Christine Chen, and I am a staff member at the Space Telescope Science Institute. STSCI is what's called the Science and Operations Center, currently for Hubble Space Telescope, and will also be the Science and Operations Center for James Webb Space Telescope. So there's a lot of expertise in Baltimore for JWST. So I'm really excited to talk to you today about JWST and particularly about exoplanets. I've heard that you've learned a lot already about the history of JWST and also observing in the infrared. And so I'm going to tell you more specifically about exoplanets, try to give you a little bit of a history for what people know about exoplanets and what we're hoping to learn from JWST observations. So when I think about our place in the universe, home is our solar system, and we're all familiar with the planets in our solar system, from the terrestrial planets, Mercury, Venus, Earth, and Mars, to the giant planets in the outer solar system, Jupiter, Saturn, Uranus, and Neptune. And actually in between, and around those planets, there are collections of smaller bodies. So for example, there's the main asteroid belt, which is between Mars and Jupiter, and then what's known as the Kuiper Belt in the outer solar system. So you may be familiar with the Kuiper Belt in that Pluto is probably the most famous member of the Kuiper Belt. It was originally, for a long time, people talked about Pluto as a planet, but it got demoted when it was realized that it was, one of a large population of objects in the outer solar system. So it is now one of the larger Kuiper Belt objects that are known. And so just to let you know, the way that space dust comes into this is I'm particularly interested in studying asteroid belts and Kuiper belts around other stars, because what happens is essentially those objects can collide into each other or into planets and create dust. And you can do a lot with the remote sensing of that dust. But I'm actually here today to tell you mostly about exoplanets, which are the larger objects in all of the exoplanetary systems, although I'll show you a couple pretty pictures of these dusty disks around other stars. So I think this is always our jumping off point for trying to understand what our place in the universe is and trying to understand whether or not there are other planets around other stars and what their potential is for supporting habitable life or life on other planets. So we think that, planets should be very common. And this is because we think that their formation is a natural consequence of the star formation process. So this chart here shows you basically how a star is thought to form, in our galaxy. So you can imagine that there is a dark cloud. So this is a cloud where there's a lot of gas and dust, and it's a region in our interstellar medium that just has more material than other places. So it could be one of these dense cores. For the most part, many of these regions there's a balance that happens between, there's mass associated with the core. So it's trying to collapse. But at the same time, there's heat energy associated with it, which creates a pressure, which supports that core against gravitational collapse. But if you have an overdensity, you have a lot of material in a core, then it can overcome that pressure and actually start to collapse to form a star. You can imagine that as it's collapsing, that these clouds probably have a tiny little bit of spin associated with them. And so as they collapse, you can sort of think of like an ice skater who is spinning, and as they pull their arms in, they move faster and faster and faster. The same thing happens when you form a star in the interstellar medium. So what essentially happens is the star starts to spin up, but it actually, because of the spin, you can support a disk of gas and dust that's sort of made of the same material from which the star formed around the star. So in the next phase, you have what's called a protostar, in which you still have a remnant amount of material from the envelope that's collapsing and accreting onto a disk, which is also sort of accreting onto the star. And instead of everything just funneling onto the star, sometimes you can gravitationally sling material both above and below the star to form these bipolar outflows. And this disk then becomes the place where the planets are expected to form. And so naturally they should form in a disk, and they should all revolve around the sun or the star in the same direction, the way that the planets do in our solar system. So in this T-Tauri phase, you still have a very gas-rich disk. Over time, all of the gas in that disk accretes onto the star or onto planets, and you're left over with the planets that have formed by phase E, like all the planets that have formed, and you may have these leftover asteroid belts and Kuiper belts that are colliding to create these dusty rings. And then finally, the mature stage is this young stellar system in the last panel, where you have the star and the planets, and it's cleared out most of the rest of the material. So I just wanted to say a few words before we go on about solar system planet formation. So we know quite a bit about how the planets in our own solar system formed from studying the planets themselves, and also from studying asteroids and Kuiper belts and comets and all those kinds of things. And we think that essentially planet formation happened different ways depending on which planets that you're looking at. So we think that the giant planets, Jupiter, Saturn, Uranus, Neptune, formed through a process called core accretion. And so essentially you initially start with all these little tiny dust grains that stick together and build successively larger and larger objects, until by an age of 1 to 3 million years, you've formed a core. So this is like a rocky core. It's about the size of the Earth, for example. And it's preferentially sort of taken the dusty material and formed these large objects. But there's still gas left over behind in the disk, and then that gas accretes onto the planet to form the envelope or the atmosphere of the Jupiter-like planets. And that accretion happens at a later age, maybe 10 to 30 million years. This is different from how the terrestrial planets formed. We think that by a few million years, that you had the formation of kilometer-sized bodies. Remember, the environments where terrestrial planets they're much hotter. And so it's hard to retain the gas in the disk in that area. And so really there's much more dusty stuff compared to the gas. We think that essentially these kilometer-sized bodies, they collided and grew into what are called oligarchs. These are objects that depleted their area of the disk, and they were the size of maybe Mars. And then at late ages of 30 to 100 million years, you had these giant impacts that, for example, formed the moon in the Earth-Moon system. And so by times later than that, you have the fully formed solar system. So this is just a chart showing you sort of what we know about the demographics of exoplanets today. This plot shows you planet mass as a function of orbital period, and each of the dots represents a planet that we've learned about today through observations using both ground and space-based telescopes. So we know of about 5,750 planets today, and exoplanet astronomers really use multiple techniques to find these planets. Radial velocity, this is also called the wobble technique. Transit, this is when the planet goes in front of the star. And direct imaging is when you take a picture and you can see the planet apart from the star. And the different techniques have different fortes. You can see in this particular plot, it's color coded by dots for which technique. So the radial velocity technique that I'm going to tell you more about, you can see they're the black dots, the transits are the blue dots. The direct imaging, they're much fewer. They're the orange dots. And so those are the techniques that I'm really going to talk about. And then I'll talk about how this translates into JWST observations in the first year of operations. So, the science of exoplanets really began in the 90s with the use of what's called the Doppler technique, or this wobble technique. And one of the first very prominent discoveries was the discovery of a planet called 51 Peg b. So the host star's name is 51 Peg, and the little b designation is the planet itself. So this chart on the left left-hand side at the top shows you what our inner solar system looks like. And then you can see 51 Peg outlined in red for comparison. And you can see that the planet is much more massive than any of our terrestrial planets, and it's located much closer to the star. But this was the very first planet around a solar-like star that was detected. And the astronomers who made this discovery, Michael Mayor and Didier Queloz, they were awarded half of the Nobel Prize in Physics in 2019 for this discovery. But you can learn more about that discovery by looking at the Nobel Prize website. So this chart shows you how these discoveries are made. So this is the Doppler technique at work. So essentially there is a star and a planet that are both orbiting about a common center of mass. And in this particular picture, it's the observer in the observatory sees the system edge on. And so we're looking sort of sideways at that picture. So the star doesn't stay still. It's actually orbiting just a little bit about that common center of mass. And so what happens is as the star moves toward the observer, it just like with the Doppler effect, it squishes the light waves from the star and creates blue shifted light. And then when the planet is moving away from, or the star is moving away from the observer, it stretches out the light waves, creating what's called a redshift. And so the observations that the astronomers make are sort of shown in this chart, like at the bottom, where you see this curve that's partly blue and partly red. So you have the radial velocity, so that's how fast the planet's moving toward or away from you as a function of time. And so you see this periodic behavior where first the star is moving toward us in the orbit, and then it's moving away from us. And so that's the wobble signature that they look for in these radial velocity measurements. So you can actually learn quite a bit from the radial velocity measurements about the planet, perhaps more than like you might have guessed. So the left-hand inset image shows you the real data of the discovery of 51 Peg B. And you can see there's that, again, that periodic velocity signature. So one of the things that you can see right away is that you can measure the orbital period of the planet. So this is the time that it takes for you to go from one point into that orbit to go around and then come back to the same point again. And so it would be like going from peak to peak in the velocity diagram there. So you get the orbital period of the planet. The other thing that you measure is the stellar radial velocity, so how fast the star is moving towards and away from us. And we can use that information as well to help us learn about two things. So not only the orbital period of the planet, but also the mass of the planet. So essentially what you can do is you can take the period of the planet, the mass of the star, and then learn what the semi-major axis of the orbit is, so how far away the planet is from the star. And then you can apply Newton's law of gravitation in the orbit equation to then figure out what the velocity of the planet is moving about in its orbit. And then finally, you can use the fact that the two objects, the planet and the star, have the same momentum to figure out what the mass of the planet is. So I just wanted to highlight that you can use basic dynamics to figure out key properties about the planets. So when 51 Peg B was discovered, it was really emblematic of a lot of the first discoveries made using the radial velocity technique. So going back to that chart again, showing you planet mass as a function of orbital period, 51 Peg and a number of the objects that were discovered early on were in this red circle. So these were objects that were both very close to their host stars, so less than 0.1 AU away, meaning that they have orbital periods of like 10 days, but they were still quite massive, as we said, like Jovian planets. And this is really a selection effect of this technique. So, you know, if you're staring and monitoring a planetary system, if the orbit's shorter, it's easier to catch the planet. And then, of course, if it's more massive, then it creates a larger radial velocity signature and makes it easy to detect. And so these hot Jupiters, as they're called now, were totally unexpected when they were discovered because there's nothing like them in our solar system. And they're really too massive to have formed so close to the star. And so this was the first time that people began to think that maybe the planets that we see, these exoplanets, where we see them now is actually not where they formed, but they have somehow migrated there today. And so it's not 100% agreed upon what the migration mechanisms are. But for example, in this particular case, we know that they couldn't have formed there, so they must have formed further out and then come in by some process that we don't understand too well yet. The other really interesting discovery from these radial velocity surveys was what's called the mass metallicity relationship. So this is basically saying that whether or not you have planets and how big the planets are depend on the metallicity of the host star. So astronomers are a little bit funny. Whenever they say metallicity, they mean all elements that are heavier than hydrogen and helium. And when you think about the planets, particularly like the terrestrial planets and the cores of the giant planets, they are made out of what astronomers would consider metals, so things that are heavier than hydrogen and helium. And so it makes sense that you might find more planets around stars that are more metal rich, because it means that those planetary systems, those stars, they have more material to form planets from in the first place. So this was actually an empirical observation that was made from studying the host stars of these radial velocity planets. And so you can see in this chart here, there was planet fraction plotted as a function of stellar metallicity. Astronomers in particular, they use iron abundance. So that's the Fe/H. And you can see that as you increase the stellar metallicity, the fraction of systems with planets goes up. And not only that, but the mass of the planets in those systems also increases. That's the mass metallicity relationship. And essentially, this supports the idea that the way that planets form around other stars is through a similar process as in our solar system. So we talked about how the giant planets formed through core accretion. So based on these observations, we think that planets around other stars also formed through core accretion. The Jovian planets around other stars formed through core accretion. So in the past, couple decades or so, astronomers have also begun using what's known as the transit technique. This technique is slightly different. It relies on a very special viewing geometry for the planetary system. So in this particular case, the planet has to go in between the star and the observer. And so what happens is basically the planet blocks out the light from the star, and it creates a little dip in the light coming from the star. And so that's what this cartoon is meant to show, is that you can see the planet orbiting around the star, but what you see in the light intensity is sort of this constant signature and then a dip when the planet goes in front. And then once it passes, it goes back to being the same brightness. So just like with radial velocity planets or wobble planets, we can learn a lot from the transit observations about the properties of the exoplanets. So you can imagine, just like with the radial velocity planets, you can also measure the orbital period, because the orbital period is the time that it takes for the planet to go around the star once. So you can imagine that's from when the planet blocks out from the light from the star, goes around once and comes back and blocks out the light from the star again. So that's the orbital period. But there are other things that you can measure as well. One is exactly how much the light from the star is dimmed by the planet going in front of it. In this plot, that's that delta F, that's measuring the trough of the light that you lose from the planet going in front. And then the other thing that you can measure is how long that transit takes. So the delta F is particularly important because that tells us something about the radius of the planet, so how big the planet is. So if you look at the percentage of that dip, delta F, compared to the ordinary brightness of the star when it's not blocked by the planet, that ratio is governed by the geometric size of the planet compared to the star. So the radius of the planet over the radius of the star squared. So this means that in the transit observations, you can measure how much the light from the star dims, that's delta F over F. And then if you know the radius of the star, you can calculate what the radius of the planet is. And so for transiting exoplanets, people additionally know what the radius of the planet is. And then from the transit duration, so how wide that trough is, people can calculate whether or not planet goes right over the center of the star, or if it goes a little bit above or below the center. So that's the impact parameter. So there have been a lot of really interesting discoveries that have been made using these transit observations. One of the really most interesting ones, I think, is the discovery of what's called the Fulton Gap. And this was discovered from observations made by Kepler of 1,300 planets. So Kepler, you might remember, was a space-based mission that stared at a field in the sky called, in the constellation Cygnus, monitoring, all of these stars over a period of like 5 years. And so they could essentially watch the brightnesses of the stars over that time to see if you could find the distinct fading, the little dips from the transits. And they could, for all of the planets that they found, calculate what the radii of those planets were. So they found something really interesting. So this is a histogram distribution showing the number of planets per star, as a function of planet size. And you might naively expect that, there might be more small planets than big planets, or maybe even the distribution is flat. But that's not at all what they found. What they actually found was that there were two peaks in the sizes of planets. One that sort of centered at 1.3 times the size of Earth, and another one at about 2.4 times the size of the Earth. And so that dip between the two populations is actually real, and that's called the Fulton Gap. And so Kepler then gave evidence that there are these two different kinds of planets. One, which are referred to as super Earths. So these are really rocky planets like our Earth. And the other one's called sub-Neptunes. And that's to denote that these are planets that have atmospheres, just the same way that Neptune does. So it's not just a bare rock. And interestingly enough, the fact that there are two populations of planets was actually hypothetically proposed before these observations were made. And the idea was that perhaps you start with a population of sub-Neptunes, but then you have the influence of the stars shining on the planet, dumping energy in the form of X-rays and ultraviolet photons and heating up the atmosphere, which then leads to evaporation of that atmosphere. And so over time, you erode the atmosphere away and naturally produce these two different groups. So, and interestingly, the presence of this Fulton Gap is consistent with all of these planets having rocky cores that are about 5 Earth masses, but just some of them happen to have atmospheres. But you can learn a lot more from transiting exoplanet observations than just the population demographics. You can also stare at the planet not just as it goes through transit, that is crossing the face of the star, but during the whole orbital period of the planet in the system. So, when it is, the planets go through phases. So when it's in transit, to us, that looks like it's a new moon, right? A new phase. And then as it goes to quarter illumination, and then finally, just before it swings behind the star, we would see the fully illuminated part of the planet just before it went behind the star, which is called secondary eclipse. And so there are a lot of these observations that were made with the Spitzer Space Telescope, which was very sensitive to heat. And so you could basically measure the amount of heat that came from the planet as it orbited around the star. So an interesting thing is that we think that the atmospheres are fairly, they don't rotate around the planet in sort of the same way that we think of the Earth spinning on its axis. But for example, that the side that's presented toward the star is always presented toward the star. And so this actually gives us an opportunity through monitoring the brightness of the planet plus star system to try to figure out what the brightness of the planet is in different places as a function of longitude, so in the west-east direction. And so you can see on the left on the bottom, that's a plot showing you the brightness of the system over time, over orbital phase. And so you can see the transit where you have the new moon with the dip, the deep dip, and then the secondary eclipse where you're starting to see the brightest thing, which is the star plus the fully illuminated planet, right before the planet goes behind the star. So you can imagine you can do all sorts of clever things since you know what just the star looks like, and sometimes the planet plus the star. But anyway, you can go through and try to invert the observations to show what the heat looks like as a function of longitude. And that's what this plot on the right is. So naively, you might sort of expect that the subsolar point, so the place on the planet that's just below the star, so where it's basically high noon, that should be the brightest place on the planet. But when people actually looked at these observations, particularly for this star, which happens to be HD 189733, its planet is called B, the brightest point on the planet was actually not that subsolar point. It was actually a point that was offset by 30 degrees. So you can see the bright spot is shifted to the right, sort of one grid line compared to the center. And so, there was a really interesting discovery. And so you have to think about, like, why is that side hotter? And so the prevailing hypothesis is that there are global winds on this planet that redistribute the heat around the planet. So, and then the last class of kind of observations that people make of these planets is trying to really study their atmospheres. So now we're looking at kind of the transit depth at a whole bunch of different wavelengths. So the y-axis is sort of related to this transit depth, and on the x-axis, it is a wavelength. And so you can imagine that, for example, when the planet goes in front of the star, the rocky part may block out the light from the star, but the thin skin of the atmosphere on the surface, particularly if it's clear, may permit the transmission of light from the star through the atmosphere. And then that gives the atoms and molecules in the atmosphere an opportunity to imprint their spectral signatures on the light that comes out. And so basically by stringing together this transit data across a number of wavelengths, you can perform spectroscopy and try to understand what the atmosphere is made out of. And so this plot on the left is showing you the spectra of about 10 hot Jupiter planets. And you can see there are vertical lines that are dashed that are marking out the detection of sodium and potassium in their atmospheres. And if you look really carefully around 1.5 microns at the top, there's a little dashed line that says water. And so that's where the water band is. So you could also look for water in these planetary atmospheres as well. So the really cool thing about this particular study, which was a sort of a joint project between the Hubble Space Telescope and also the Spitzer Space Telescope, is that you could learn a lot about the atmospheres. So on the blue side, on the left side, the short wavelength side, by looking at the slope of the light, whether or not there's more blue light than red light, so a slope that starts high and goes down to the right, as you see for 189733b, the second one from the bottom, that indicates that the atmosphere is relatively clear. And then by contrast, if you go up to WST 12b, you can see it looks really flat. So the reason why is that the other one looks flat is because it probably has clouds and hazes in its atmosphere that make it difficult, that sort of block out the light from the star and make it difficult to do remote sensing on it. So one of the really interesting observations by combining the HST and Spitzer observations was, one, from Hubble, you could see whether or not the atmospheres were clear and cloudy. And then from Spitzer, you could see whether or not there were signatures from molecules like water. And one of the things that was found was that the hazy atmosphere planets were less likely to have strong water signatures. And so it's thought that that's a selection effect, that probably the atmospheres are usually water rich, but sometimes we just can't see the water because of the clouds and haze in the atmosphere. And so the other thing that's interesting is that, some of these planets that are clear have a lot of water in their atmosphere. And so that tells us something about the amount of metals in the planet, because oxygen is an element that's heavier than hydrogen or helium. And it tells us that it's additional evidence that these planets formed through core accretion, and that the gas was probably accreted relatively late in the disk's lifetime. So I'm going to move on now to the last technique, which is called direct imaging. And this is sort of maybe the most intuitive of the the techniques. In this particular case, you're taking a picture of the star, but one of the challenges is that the star is extremely bright compared to the planet that's next to it. And so to try to overcome this problem, what you want to do is subtract off the light of the star to reveal the faint planet. And so that's the technique that astronomers use in direct imaging. So on the left-hand side, you see here, for example, this is an observation of a star with the planetary system around it. And that is the raw data. That is what the image looks like. And it's really hard. You can't see the planets in there at all. And then what you do is you go and you take, for example, an observation of a specific other star. And it should look just like the host star in the planetary system. They're both unresolved points of light. And you can subtract off the other star from your star of interest to look for the planet. So that's what's called point spread function subtraction, because the unresolved star is called the point spread function. And you can see how you can do better. But people are now applying what are called advanced PSF subtraction techniques, where instead of just using one reference image or one reference star, you use a library of reference stars that sort of sample like all the different ways that the mirror could be. And so you can get a much more precise subtraction of the host star. And you can see indeed with this advanced PSF subtraction, in this particular case, it reveals the presence of 3 planets in this planetary system. But astronomers also use another technique to try and facilitate the detection of the planets. Not only do they do this PSF subtraction, but they also use instruments that are called coronagraphs. And coronagraphs basically block out the light from the central star. So coronagraphs were originally developed to study the corona of the sun. And essentially what you do is you place an occulter over the bright disk of the sun, and that blocks out the light from the star, and it lets you look for the faint glow of the corona. So this happens naturally, for example, during a solar eclipse. But in our particular case, we can use these same techniques to block out the light of a host star and then look for a nearby planet. So in general, you can see, oh, sorry?
Sorry, it's Bronwyn. Can you go back to that slide real quick?
Sure.
So in looking at the middle picture, I mean, would scientists be able to ascertain from this picture that there are three planets around?
No. So this is a remarkable, this is a wonderful thing about data, particularly from like Hubble and JWST. Like once you take data, basically it sits in your archive. And people get smarter over time about how to do PSF subtraction, for example. So when this data was originally taken, I think it was in like 1998, it was taken with the intention of looking for a planet, but nothing was seen, because you can see it's really hard to dig anything out near the star. But then, people are so inventive that they come up with like, more and more ways to do things better, right? And so actually one of my colleagues at Space Telescope, Remy Sumer, developed a technique to use not just one reference star, but a whole collection of reference star observations. And so that he could improve the fidelity with which you subtract out the star. And so he was able to take this old data and basically reveal 3 planets, around that star that hadn't been known before. But in all fairness, like there had been some ground-based observations that had pointed to the existence of these planets. And so he went back and went, oh, they should definitely be in this NICMOS data. So how can I pull them out? And so essentially that's what happened. So.
Great, thank you.
So if we look at this plot again of planet mass as a function of orbital period, you can see the area in this sort of diagram that this technique works well for. So since you're blocking out the light of the star, you can imagine it's hard to find planets that are super close to the star. So they tend to be further away, like at the distance of Jupiter or Saturn or larger. And they also tend to be more massive because the more massive ones are brighter. So most of the cutting edge work that's done today right now is performed from the ground using specialized instruments on big 8-meter class telescopes. So the US owns the Gemini Observatory, and there's an instrument called the Gemini Planet Imager. It has one of these coronagraphs, and for example, has been used to search hundreds of stars looking for planets. so there have been some planets found with this technique, and the lessons learned are essentially that the planets that are found this way are more likely to occur around higher mass stars, so things that are bigger than our sun by about 50%. And then the integrated occurrence rate, so this means all the planets they found divided by all the stars that they looked at, is about 10%. So there were a couple of cases like HR 8799 that I just showed you where there were multiple planets. And so all those 3 planets would count separately. But just to give you a feeling for how different this technique is from the others. But they have learned really interesting things. So if we think about stars and giant planets, there's actually a category of objects that lie in between. These are called brown dwarfs. And these brown dwarfs are kind of like failed stars. What makes stars stars is that they have ignited thermonuclear fusion in their cores. Brown dwarfs aren't massive enough to support a fusion of hydrogen into helium in their cores. They fuse deuterium at first, and then they run out of deuterium and they fade over time. But what they learned from looking at brown dwarf distribution or these companions around stars was basically that the brown dwarfs and the planets had different distributions. So the planets, of course, had smaller masses, but if you looked within that category, there were more small things than big things, unlike brown dwarfs where there were more big brown dwarfs than little brown dwarfs. And then similarly, the planets were at smaller semi-major axes, distances from their stars, whereas the brown dwarfs were further away. And so it actually suggests that the 2 populations of things, planets and brown dwarfs, form through different mechanisms. So planets, again, form through core accretion, but then brown dwarfs form through another process called gravitational instability, which is much more like stars, where you have an overdensity of material that just collapses directly to form the brown dwarf. So this is kind of where we get to things that I really love and study all the time, which is, some planetary systems are a little bit more rich in terms of the diagnostics that you can use to study them. So when I think of an exoplanetary system, in my mind, this is kind of what I think of. So it's a thing that has a host star and not only has planets, such as the Jupiter planet here, but it also has, asteroids and comets. And I was speaking to you before about how you have collisions between those things and they create dust. And then you can study that dust to learn a whole lot more about that system. So things in particular that you could learn are small planets can create structures in the dust. And so you can find small planets that you wouldn't be able to find any other way by looking for their fingerprint signatures in the dust. And also the dust is easier to study through remote sensing. And so you can learn about the composition of the dust. So this is unlike when you study the planet and you measured the mass and the radius, and that told you about the bulk composition, but not the detailed chemical composition. So by studying the dust, you can learn about the detailed chemical composition of the material. So one of my favorite stories is this star called Beta Pictoris. This is a very famous, what's called debris disk. So one of these dusty disks around a main sequence, a middle-aged star. For example, this happens to be a slightly younger one. But this disk had been imaged starting in the 90s. And the remarkable thing about these disks, these debris disks, is that when you study them and you apply higher and higher angular resolution to them, you see finer and finer structure that tells you about the presence of planets. And in this particular case, it was that there was a tilted inner component to the disk compared to the outer disk. And one of the hypotheses for why this existed is that there was an unseen planet that was perturbing the dust and creating the signature. And indeed, that planet was later discovered through observations from a ground-based telescope. And you can see in the bottom picture, it's a composite of the image of the planet as it's orbiting around the star and then the disk further out. So the planet was first seen in 2003. You can see it on the left side of the image. And then it went behind the star and popped back out in 2009. So you can imagine that for these particular planets, you can also study them spectroscopically to learn about their properties. This is a nice movie that was produced from GPI observations showing you the orbital motion of the planet around the star. But the more modern observations, this happens to be a chart here on the right showing you the spectrum of this planet taken in the near infrared. So you can see from 1 to 1.8 microns, and then 2 to 2.5 microns. You can learn a lot about the composition and the properties of the atmosphere. So one of the things that you might notice on the bottom is there's a lot of squiggles in the black line, and that's actually a real astrophysical signal. It's not noise. That's actually a spectral signature from carbon monoxide that's seen. That information can be used to, for example, measure the carbon to oxygen ratio in the system. By modeling the overall shape of the whole spectrum, you can estimate how hot the planet is, how much iron, how much metals are in there, and all sorts of properties. The key thing about this particular planet is that the C to O ratio that's measured from the spectrum is similar to that of the host star, and it suggests again that this giant planet formed through core accretion. So now I'm going to go on to JWST in the last few minutes. So JWST really builds on the legacy of Hubble and Spitzer. And so I've shown here all three telescopes to scale. And so you can see Hubble on the left. It's an ultraviolet to near infrared telescope with a 2.4 meter diameter primary mirror. And that's actually in a low Earth orbit. And then you can see Spitzer in the middle for comparison. This was really a far infrared telescope operating from 3.6 to 160 microns. It was much smaller, only 85 centimeters. And it was actually located in a heliocentric orbit. So it orbited around the sun just like the Earth. And it actually slowly fell behind the Earth as well. So it was Earth trailing heliocentric. And then, of course, we're all super excited about JWST, which really overlaps in wavelength space compared to both Hubble and Spitzer, going from about 0.6 to 30 microns. And it has a much larger mirror, so 6.6 meters compared to Hubble and Spitzer. This also translates into a larger collecting area, which means that it's much more sensitive. And it's located at a slightly different place. It's actually at the Sun-Earth Lagrange 2 point, which is a stable point and that's beyond the orbit of the moon. So it'll be far away from Earth. So I was just going to go through some of the programs to give you a flavor of the work that people are doing. So predominantly astronomers are going to be using JWST to perform direct imaging and also transit observations. And there are a lot of really beautiful circumstellar disks, these debris disks that I've been talking about, that have been imaged, for example, with Hubble Space Telescope. And you can see that many of them have gaps or all sorts of structures in them. And we don't know whether or not these structures, whether they're created by planets. And so essentially JWST affords us an opportunity to search for more sensitively for planets. Down to Saturn mass planets, whereas the ground-based instruments were looking at things that were more like a couple Jupiter masses or so. And you can even get down to, I think, perhaps even Neptune planets, particularly if you're looking at lower mass stars. So searching for planets that create structures and disks is going to be a major theme. It will be one of the things that JWST will do. JWST is also going to be a very powerful tool to explore transits. And so there's actually a lot of targets that are going to be explored for transit. So this particular diagram here shows you planet radius on the y-axis as a function of equilibrium temperature. And each one of those dots represents a target that's going to be observed with JWST. So you can see that JWST is going to study everything from hot Jupiters in the top left corner to, so that would be through transit, to cold gas giant planets. So that's more like the direct imaging technique. And then down, as you travel down the diagram, you go down in mass, So things that are about the temperature and size of Earth, and then moving inward to terrestrial planets that are really lava worlds. They're molten because they're so hot. So you can imagine that the JWST observations are really going to improve upon the spectra that were carried out with Hubble Space Telescope. And so they're going to look for a lot of different species. So not just water and CO, but also methane, carbon dioxide, acetylene, HCN, and ammonia. And so really trying to measure the C to O ratio for a bunch of planets to understand where they formed. Do they form beyond the water ice snow line the way that our solar system giant planets did? They'll study the height and composition of clouds and hazes and how the atmosphere varies with longitude. And then they'll also, for some select planets that are in very elliptical orbits, that means that sometimes they're very close to the star and sometimes they're very far away. And so the amount of heat that falls onto the star, onto the planet from the star changes. And so for those systems, they can see how the atmospheres respond to the changing light from the star, the changing intensity of the light. So for transiting exoplanet programs, there's going to be about 68 of these observed. And so the diagram on the right shows you kind of how they're going to be doing this. So each one of these points, again, is a planet plotted in planet equilibrium temperature space on the y-axis and planet mass on the x-axis. And so all the blue dots are things that are going to be observed in transit. So again, that's the time when the planet passes in front of the star. And then there's going to be a couple of, there's going to be another set of planets that are going to be observed in what's called secondary eclipse when the planet passes behind the star. So you see the frontally illuminated, the hot side of the planet going behind the star. So that's when you no longer see the planet anymore, and you just see the radiation from the star. And so you can learn about the heat signature that way. And then for just 3 targets, you can see that they'll look at the light from the planet as it goes all the way around. That's what the phase curve means. So from transit through crescent, gibbous, all the way to eclipse, and then coming all the way back to transit again. So I just wanted to leave you with one last picture. This is a picture of a system called TRAPPIST-1, which is probably going to be the most studied exoplanet in JWST Cycle 1. This planetary system lives around what's called an M-type star. This is a low mass star, which is a fraction of a mass of the sun's mass, maybe half or something like that. And so it is not as bright as the sun. This particular planet, or this particular planetary system, has been discovered to have 7 planets that are orbiting around them. And the 7 planets are actually in the habitable zone for that particular star. So the planets have a variation in distances from being Earth-like to further out than Mars and closer in than Mercury. And so you can imagine that we expect there to be a great diversity in what the atmospheres and the surface properties of these planets are going to be like. And so that's really the goal, is to characterize them and to try to understand how they're similar to or different from the planets in our own solar system. So with that particular picture, I'll stop, and I am happy to answer questions.
Thank you so much, Christine. You can unshare and we can come back together. And let me make sure that I have a spotlight on you. We do have a question. Robert O was mentioned that in your talk, you referred to the star, but aren't there a lot of systems that have double stars? And does that alter the calculation?
Yeah, absolutely. That's correct. So there are a lot of, there are a number, and I don't know what the exact fraction is, of planetary systems that have been seen to orbit around 2 stars. They're called binary systems, are actually quite common, in our galaxy. So perhaps it's not surprising that we find planets in these binary systems as well. there are reasons for why, when people are studying planets, why sometimes when they choose things to look at, they choose deliberately not to look at binary stars. So for the transiting technique, people are pretty agnostic because they can sort of correct for the effect of the second star and still back out the properties of the planet, and that's all well and good. But it turns out, for example, when you're using the direct imaging technique, you can imagine if you have a bright star and one that is occulted and then another one that's nearby, you still have the full glare of that star that's nearby. And it's very hard to subtract out. And so it means that you cannot search as sensitively in that binary system for planets or characterize the planets as well. So this is also true for radial velocity. My impression is that they essentially typically look at single stars because the signature, the radial velocity signature from the companion star would be so big that it would be more difficult to find the planet because you have to remove that signature from the second star as well. So absolutely true, planets around binary star systems, but there are times when astronomers specifically choose to only look at single stars because they are easier to understand and subtract out.
Thank you. Thank you for the presentation. Anybody have any other questions for Dr. Chen? I find it amazing that we can find so much information about the individual planet from just looking at the light signature, so to speak. It truly is amazing how much data can be extracted out of what we can see. I had a question about the metallacity of our own sun. Is that what they use to create the baseline for
That's
that?
correct. Yeah. So implicitly, whenever you see that that it had it said Fe for iron divided by H for hydrogen, and it was in square brackets, that's always implicitly comparing the metallicity of the other star to our sun, and it's done on a logarithmic scale. So basically, everything's compared to the sun. So solar metallicity is kind of like the 0 point. And then anything that has like a positive value for metallicity, that's something that's super solar, that has more metals than our sun does. And conversely, anything that has a negative value for metallicity is something that's subsolar. It has less metals than our sun. Absolutely.
And Robert is following up, is the launch date firm on December 18th?
It is. So everything is progressing well right now. Essentially, the observatory is in Kourou, the Ariane Space site. Essentially, it's all going very well. So all the initial observatory checkout when the observatory got there is proceeding very smoothly. I think the last thing I heard was they were about to move the telescope, the observatory, to a different building to put hydrazine into the thrusters on the observatory. These are used for the station keeping of the observatory at L2. My impression is that they are, they go to move the telescope, the observatory into the nose cone of the rocket, into the fairing. I think that happens in December. So they're actually, some of the activities have gone so well that they had, I think, a number of days, maybe a couple weeks of margin in case something went wrong. And they didn't need to use any of that time at all. So everything is going extremely well. And we really do anticipate the launch to happen on December 18th. There could, of course, be weather delays, but we won't know about things like that until we get there.
Is the launch going to be online?
Yes. So I understand that, I presume that it will be shown on the NASA channel. But yes, I believe it is going to be broadcast live.
And are you worried about any aspect of the deployment, or what aspect worries you the most?
I'm not super worried. And this is because, I know that people have rehearsed a lot. They've tested the observatory a lot and they have rehearsed a lot. So one of the reasons why space-based missions take so long to come to fruition is that essentially they have to test all of the parts in isolation and then in concert together. And so like this process of testing just takes years and years and years. So for example, the instrument that I worked on, the Mid Infrared Instrument, was delivered to Goddard, shoot, I can't remember, sometime maybe around 2014. It was a number of years ago. And so even though the instrument was ready, essentially they first put it into there's a module that holds all the instruments together. They test that. They, attach that to the telescope. They test, the light going through the telescope to the instrument. So there's all these layers of regression testing that happen to make sure that everything is working together. And I know from a personnel standpoint, the staff at the Institute have been rehearsing really hard for launch and commissioning. And so, and during these exercises, they get problems thrown at them where things don't work perfectly, and they have an opportunity to try to troubleshoot and figure out how to fix things. And so, at this point, everything is so well tested, and everyone is so well rehearsed that it helps me rest easy that I think that things will go well.
And Oliver and Katie are interested. What elements did you say were measured by the metallacity again?
Yeah, so you can look at a number of different elements, because you can imagine that not everything goes up and down in concert, right? So if you look at the sun, it has a distinctive sort of fingerprint of metals, like a certain amount of iron compared to like sodium compared to potassium, right? And so typically what astronomers do is they use iron as a proxy for everything. And so they really measure like how much iron is in the star. And they compare, the iron abundance in the other star compared to like our sun. But you can imagine going a step further and looking at a lot of other elements too. And, looking to see whether or not the metals, all go up and down in concert together compared to the sun, or if just some go down and some go up. And so there's some really exciting work that some astronomers have done looking at how the metal abundances across different elements change for different kinds of planet hosting stars. And so for example, they see that sort of the rock bearing elements might sometimes be missing more than the lighter elements. And so or present more than the lighter elements. And so, some people have hypothesized that is a signature for planets, falling into the star, and adding its metals to that in the sun and changing the metallicity of the star. So there's a lot of cool stuff you can learn by looking at the metal abundances, not just of iron, but other atoms as well.
What did you say that was being put into the system to keep it at the Lagrange point? Because I believe that was a question we had from last week, how it was going to stay in the Lagrange.
Yeah, okay. So the Lagrange 2 point is this sort of quasi-stable point in orbit. Remember that, we kind of have like an n-body problem here. There's the sun, there's the Earth, and then there's the moon. And so basically there's this point, it's called the Lagrange 2 point. So basically from the Lagrange 2 point, you can look back and see the moon, the Earth, and the sun kind of, all lined up. And it's stable, it's quasi-stable, which means that it doesn't take too much effort to stay there. But over time, the observatory would drift out of this L2 point because it's not perfectly stable. And so basically what happens is the observatory carries on board thrusters that help it to basically stay at the Lagrange 2 point. It's actually in orbit around the Lagrange 2 point. And so the thrusters help to maintain its position. So one of the things about JWST is that it has a fixed lifetime. And the lifetime is really set by how much fuel, how much hydrogen is on board the observatory to station keep it at L2. And so one of the critical things that I'll be watching for during launch is how well the Ariane 5 rocket inserts the observatory on its way to the Lagrange 2 point. So if it does a really excellent job, then essentially you don't have to use the observatory's thrusters at all to put it in just the right place. But if it goes sort of nominally, then you might have to use the observatory's thrusters to put it in the right place in orbit around L2. So depending on how you use the thrusters, in that initial period right after launch, the mission lifetime could be anywhere from 5.5 years, which is the requirement. The observatory has to observe for at least 5.5 years. But if you do a really good job, you could imagine the observatory lasting more than 10 years. And so that's something that I'll be really curious to see. And then we'll know the answer to not too long after launch, like within a day or so.
And will James Webb be used for macro physics, deep space origins of universe, dark energy, etc.?
Absolutely, yeah. And that was actually the original killer application, if you will, for James Webb Space Telescope. So James Webb Space Telescope was actually conceived of, people started dreaming about this large infrared telescope actually in the 1990s, even before Hubble launched. But in order to get a facility like this approved through Congress, for example, and the astronomical community has to sign on, and so there has to be a science application where the observatory will be able to do superb science that no one's ever been able to do before. And so it's really, for JWST, the first one was looking at the first galaxies. And so basically, the reason why people sometimes think of JWST as the successor to Hubble is because basically, when people were first thinking about JWST, they didn't know if you could see the first galaxies, like if they would just look like points of light, or if you would actually spatially resolve them into spirals or irregular structures or whatever, something more than a point of light. And so that's actually what the Hubble Deep Field told us, was that you could see the galaxies all the way to pretty much the Big Bang. And you could know what their size was, and you could know that they would be resolved in the infrared. And so basically that was the original sort of killer app for JWST, was studying the first galaxies. And, as you've heard in your talk on the infrared, that means that you can actually see further with JWST than you can with Hubble, because the light from these distant galaxies is redshifted. And so the visual light that the galaxies produce can be shifted out of the wavelengths at which Hubble is sensitive to. So we expect to see new galaxies that we haven't seen before, that are even further away than the ones that Hubble has seen. And so that is the other, I would say, major science area for James Webb Space Telescope. Absolutely.
All right. Any other questions for Dr. Chen? I do. What do you hope? What do you hope that James Webb will see? What are you hoping for?
Yeah, my particular science interest is, I'm really interested in water and the potential for life on other planets. And, we think that water is really important for that, because it is certainly for life on Earth. And so the infrared gives access to a slew of water emission lines, particularly when that water has a temperature of 500 to 1,000 Kelvin, kind of like the temperature of the terrestrial planets in our solar system. And so I'm hoping to learn about water, like the potential for water in the terrestrial planet zone, and also actually in the outer parts of planetary systems too. So when we look at Pluto and some of the other big Kuiper Belt objects, we know that they're icy because we can see in their reflected light, we can see features from water ice. So I'm really interested in looking for water ice in the solid form in Kuiper Belts around other stars, and then also for water vapor in the terrestrial planet zone.
Well, we can't wait to for JWST to get up there and start beaming back some pictures. We know that it's going to take a month to get to the Lagrange point, and then another 6 months for it to start beaming back after it's deployed. So we'll be waiting with bated breath along with you to see those first images. And thank you again. Again, next week we are going into the birth of stars, and so please join us back here on Thursday for more explorations into space with the James Webb experience. Thank you for joining us. Thank you, Dr. Chen. Stay well, stay curious, everybody. Good night.
Night.
Thank you, Christine.